All right, let's get started. So last time we were talking about the median finding problem and more generally the selection problem. So in this problem, we're given a list of numbers, not sorted. Otherwise, the problem would be too easy. And we're asked to find we're also given a number k, and we're asked to find the kth smallest element. So for example, if k is s over 2, this amounts to finding the median. The immediately obvious algorithm comes to mind. Easy one is that you just sort the input array, and go to position k, and return the value in position k. And this, of course, is very easy to implement and great, but we know that sorting takes n log time. Like merge sort takes n log time. So, okay, so we're gonna now think of come up with a divide and conquer algorithm that's gonna actually work in linear time. Okay. The idea of the algorithm is the following. First, pick a pivot, and we'll talk about how to pick a pivot element. We'll talk about it in a few minutes. But for now, let's just say you picked the pivot element. Okay, and we're working with this example. So a pivot element is you picked 5, right? You picked 5. Then you, after you do that, you pass through this array, and each item you throw it into one of 3 buckets. The 3 buckets are SL, so everything to the left. If you imagine a sorted order, everything to the left of the pivot or smaller than the pivot. SR, everything to the right of the pivot or bigger than the pivot. And SV, everything that is equal to the pivot. And if we go through this list, then we get this these buckets. And the important thing is really we're not actually going to put the buckets. We're going to count the size of these buckets, right? That's, I guess, an important point. We don't need the elements. We just need to know what's the size of each bucket. And then, like in this case, we got 3 elements, then 2, then 6. So this says that there are 3 elements less than V, there are 2 elements equal to V, and there are 6 elements bigger than V. And this lets us now answer try to answer the question of the kth element. So if k is 1, 2, or 3, we know we can just make a recursive call of selection to the left list and pass it k. If k is, for example, 4, then we know it's not in the 3 elements that are smallest, but it is then in the 5 elements that are smallest. So with k equals 4, we know it's going to be in SV, and then we can just return V, or 5 in this case. If k is 8, like if k is, so k 8, we know that it's not in these 5 smallest elements. And once we get these 5 out of the way, then the 8th smallest element in all of this is the 3rd smallest element in the right half, right? 8 minus 5, we get 3. So what we want to do in that case is recursively make a call to the right half, passing not k, but k minus the size of these elements. And that's, so in this case, 8 minus 3 minus 2. And this is basically what I described, this definition of the selection function that can be a recursive definition of it. Yeah. Yeah, so when we go here, we go to the right half and pass it 3. Then we make a recursive call, which means that now we're going to have an array of 6 elements. We're going to pick a pivot somehow, and we're going to separate that around the pivot, and then maybe we get lucky and k equals 3 will be the SV part. If not, then we'll have to recurse again. And then there's a base case, which I'm not going to write out explicitly, but when the size of the array is 1, for example, then you can stop recursing. Okay. So this is the algorithm, except I didn't tell you what the pivot, how to choose the pivot. But let's analyze its runtime to see what we can hope for here. Now, the part about going through, scanning through this list is just a linear time algorithm. So the initial scan to count SL, SR, and SV is theta n. Okay. And then if we do the recursive call, we also have to create this SL. So create SL or SR for recursive call. That's also big O of n, because actually maybe we don't need to make a recursive call. So in that case, we don't have to do it, but worst case, it's linear time. Now, the question is really, what's the size of our recursive call? What's the size of SL and SR? Right, we only make one recursive call, so it's just T of something plus O of n time. Okay, just intuitively thinking about it, it'd be great if we have an even split, or the half that we recurse to is even less than n over 2. But so if that's the case, then we can put n over 2 here, assuming even split. If it's an even split, then no matter which side you go to, then you decrease your size by 2. Okay. And anyone remember what the running time of this is? You can try it by master theorem. This is the case where D dominates. So log base 2 of 1 is less than 1. So here is n to the power of 1. So that's the term that dominates T of n. Okay. So if we manage to get an even split, then we have a linear time algorithm. But we don't necessarily get an even split. So in the worst case, for example, V is always the largest element. Here we split around 36. Well, that's kind of, oops. We split around 36, that's gonna suck, because then SR, everything larger than 36, it's just gonna be empty. And SL is gonna be just the size of n minus 1. So then we'll have a recurrence of T of n equals to T of n minus 1 plus O of n. And this we actually solved in a previous lecture. We used the unrolling technique there. That's actually n squared. All right, so then you're even worse than sorting. Okay, so that's really important about how to pick a pivot. The idea is pick a pivot at random. Pick V randomly. The idea is that if you pick V randomly, then yes, you might get the very largest or the very smallest, but there's not, it's unlikely. Most likely you'll get something that's sort of in the middle. That's the intuition. Let me be a little more precise. This is main idea. Okay. Let's say V is good if it's within the 25th, 75th percentiles of S. And meaning there's like if you sort S, then you have the quarter smallest, 25% smallest elements, the 25% largest elements, and V is good if it's not in there. V is good if it's in the middle 50%. Okay, that's what we're going to call good, and I'll explain why that's good in a second. Okay. Then, so what happens if we're guaranteed it's good? Then T of n is so we're going to make again one recursive call plus O of n. So what's the size of that recursive call? If V is good, like let's say V is at it's barely good. Let's say it's at the 25th percentile. That means a quarter will lie in SL and 3/4 will lie in SR. Now, if we're unlucky, we go to the bigger half. So we go to the half that's 3/4 of the full size. That's the worst that can happen to us. So the worst here, and that's why I have the less than or equal to, the worst recursive, the worst size of the recursive call that I could do is 3/4 of all of n. And this, again, if you were to look at the master theorem, this is still all of n. So that's why we're saying it's good. Before we were assuming an even split, that's hard to do to get something right in the middle. But I've weakened the condition that even if it's not an even split, as long as we're in the middle 50% of elements, then our algorithm will still be linear time. Okay. So let's try to get a good pivot. Again, how do we get a good pivot? Here's the algorithm. Pick V at random. Do linear scan to check if V is good. Just scan, count number of elements higher than V, number of elements lower than V, and determine if V is good or not. If not good, then go to step 1. So repeat, pick another random. Otherwise we continue, and then we use the formula for selection from above. So then we go back to the algorithm we talked about, which is just to check these cases. Use V as a pivot. All right, so this is in first time in this class you're seeing a randomized algorithm. Meaning it's not algorithm here, alg. Meaning that it's not going to be, the execution is not going to run the same every single time. Okay, so now we talked about how to well, we didn't talk about it, but I mentioned that doing probabilistic analysis of running times is hard. And that's generally true. But this is going to be one example in this class that we'll see of probabilistic analysis, which is actually not too hard. It's kind of the solution is kind of elegant. So how do we do it? Right? We no longer. I mean, the worst case running time here is that we never terminate. You can just always be unlucky and always picking the highest number or something like this, always picking a bad pivot. So we can't do a worst case analysis, it's pointless. But of course, if you run this algorithm, that's not going to happen. If you get unlucky once, twice, there's kind of, the idea is you won't get unlucky too many times. Yeah. Well, so the question is, if we're already going to do a scan and check if V is good, why don't we also find a good V while scanning? There's no way to do that. If you try to think of like, what do I pick a good V? You can't guarantee it. Like you're only counting how many are smaller than this and how many are bigger than V. So maybe you can help yourself for next time and say, well, like 5, let's go back here. Let's say you picked 36. So you scan and you're like, 36 is too big. So you know for next time, you need a pivot that's less than 36. So that can help you. As we'll see, it's not going to help you asymptotically because, because it's already, we'll see the analysis, it's already good enough. It's going to give you expected running time O of n. So I think this is an important point that sometimes, when you're programming, when you're actually programming an algorithm, there are things that come to your mind that like, hey, that's a good idea. That's going to, speed up the algorithm twice. In this class, if you speed up the algorithm twice, what do I care? It's still the same asymptotic runtime. It's kind of a different way of thinking about it. So yeah, that's a good idea. But as we'll see, it's still going to be an O of n algorithm. So asymptotically, it's not going to make a difference. But yeah, once you're implementing it, then yeah, those kind of tricks, of course, can help. But I guess the point is, like in this class, we want an algorithm that gets you in the right bucket, like asymptotically, it's O of n and not n log n. And once you're in there, then of course you can think about constant time speedups. But you want to at least kind of get in the right bucket. Yeah. So if you have a reason to assume that the numbers come from some kind of nice distribution, like in your example, that they're from a Gaussian or normally distributed. Okay. then you can actually make a much better guess. So if I tell you that these numbers coming from a Gaussian, I just scan, let me see, I can probably just compute the mean on the fly and just use that as my pivot. And probably that's pretty close to the middle. At least I can prove that it's close to the middle. I can prove that it's good. So yes, if you want to, if you have a reason to assume something about the distribution, that can help your algorithm. In this case, we're not assuming anything. I mean, those numbers could be whatever, right? We're preparing for the worst case of the input. Yeah. No, V is the value in the array, and you do have the access to the value. Yeah. Okay, so let's try to analyze the expected running time here. As I mentioned, the worst case is not really interesting. So before we had T of n, now we're going to write T of with the subscript E. It's going to denote the expected time input of size n. So now what can we, how do we write this for our algorithm? Well, so it's the expected time. So I'll use the E. Okay, so what's the running time of our new algorithm? Well, it's the time. There are two parts. One is the time to find a good V partition. Plus, plus now the time taken recursively, taken by the recursive call. So the time taken on input of size at most 3 n over 4. Because we already argued that if it's a good pivot, then that's the size of the subproblem. So I'm just writing down the two steps as usual, the non-recursive part, which here is to find the good pivot and partition, and the recursive part. And we can split those separately. So like linearity of expectation, you have a expectation of sums, then that's equal to the sum of expectations. So here I can split that expectation into two parts. One is the expected time to find a good V and partition, plus, and the other part is what is the expectation of the time taken on 3n over 4. This is what we call TE 3n over 4. So we've got that this time is equal to the recursive call time plus this expected time to find a good partition. So how long does that take? Okay. How long does it take? Okay. Uh, let me give you some intuition. Let's say I'm giving you a coin, a quarter, and I'm saying, how many times do you need to flip it until you get a heads? Any guesses? Yeah. You can flip tails your entire life. Okay, so let me rephrase. That's good. What's the expected number of times you have to flip to get a heads? Yeah. 2. Okay. That's right. So let's prove that. We'll prove that lemma. There's a lemma. So on average, it has to be a fair coin means it's, it's a quarter. It's not no funny business there. A fair coin needs to be tossed twice before we get a head. So let me first prove this, and then you'll see how it's relevant to our case. Okay. So let E be the number, this number of times the expected number times we need to flip a coin before seeing a head. So let's write down what E is. Okay. So there are two possible things. One is the probability that we get head. Times, so if we get head, then these are the number of flips we used. Just one flip, we immediately got a head. The other possibility is that we got tails. And in that case, what's the expected number of flips? We will use? Well, we already used up one flip, and that didn't help us at all. And then now we're going to repeat this whole experiment. Well, we already have a variable for the number of flips that we need in expectation, and that's E. Okay. This is where the kind of elegant solution here comes from, that we can express E recursively. In other words, if I'm flipping heads and tails, I'm waiting for heads. If I flip once, I got a head, sorry, I got a tail, then this doesn't help me in the future get a head. Like I flipped the tail, okay, I flipped one coin once, and now basically I'm back to the start. I'm back to how many times do I need to flip to get a head. And so that's where this E now comes in. Okay, so this is now really easy to solve because the probability of a head is 1/2 plus probability of a tail, 1 plus E. Let's solve this. So 2E equals 2, multiply both sides by 2. So 2E equals to 2 plus E. So E equals to 2. you're curious if this is correct, you can go home, take a quarter, do this experiment like 10 times and see what your average is. On each time, flip until you get ahead, write it down, and then see over 10 experiments what your average is. You should get approximately 2. Right? Or you should probably go with that quarter to the FBI because it's not a fair quarter. And it's probably funny money. Then you can show them this proof to explain why. Okay, so how does all of this, how does this connect to picking a good pivot or not? Anybody understands the connection? Why picking a good pivot is like flipping a fair coin? Yeah. Well, so I've got all the elements and I pick one at random. And I'm saying it's good if it's in the middle 50%. So that means that, if I pick any of those middle 50%, then I'm good. If I picked any of the other 50%, I'm bad. So it's like flipping a coin. I get 50% chance to be good or head and 50% chance to be bad. If I'm good, I'm done. If I'm bad, then I try again. So this, we can go back here. This on average is repeated twice. And that's what it tells us. Now we can fill this. So let me put the end of proof here. Now, so our running time here is the expected time to find a good pivot in partition. Write that T of n, V of n, the expected time to find a good pivot is now the same time, like twice what is needed to find, to just choose a pivot. So every time we scan, right, to check that the pivot is good, we have to scan it. So we do order of n time work. And an expectation, we do this process twice. That's what the lemma showed. So we're still doing order of n work. Plus the last part there, this one. So if you compare this to, so O of n plus this recursive call to 3 of n over 4, it's the same recurrence relation as here. So here, we just assume we would find a good pivot. But now if we don't assume, if we modify our algorithm so that we are guaranteed to find a good pivot, then in expectation, the running time is still the same. So this is equal to O of n. Here you've seen so this completes this algorithm. You see a probabilistic algorithm. It's a divide and conquer algorithm. And it runs in linear time, which is much faster than the n log n time that we would have gotten by sorting. Here, the divide and conquer, like why is this divide and conquer? Well, the conquer step basically doesn't exist. It's like binary search. You just make a recursive call, and then you give everything to that recursive call. It's just one recursive call. The tricky part here is how to divide. How do you pick a pivot? In merge sort, the divide part was trivial. You just do it in half. The tricky part was how to merge, how to do the conquer in linear time. Question? That's a really good observation. So the question is, well, like, why did we, is it really necessary that we pick the 25th and the 75th percentile? What if we pick the 5th and 95th percentile? It turns out that if you look at the proof, that will also give you linear time. The constants will be different, but that will also give you linear time. But we won't get into that. The point is, the important thing is you take some fixed fraction, right? So even if you take 0.001 percentile to 99.99 percentile, that will still work in expectation. However, this 2, you might like the constants will be different. If you actually implement the algorithm, you'll see running time differences. Other questions? Okay, I want to cover another example. Everyone always wants more examples. And so I made time this semester, to give another example of a divide and conquer problem, max subarray problem. Okay. So the input here, an array A of possibly negative integers. And the output is this a subarray A with the biggest sum. Here's an example. We've got -5, -6, 3, -2, 7, -6, 2, 1. When I say subarray here, I mean like a subsequence, like a contiguous a subsequence. So for example, here, this is one subarray, and the sum here is -5 plus -6 plus 3, which is -8. Right? So that's not a very good sum. What about this guy? Here, the subarray is 3 minus 2. The sum is 1. Okay, so that's better. And there's also example, this guy. So here, the sum is 8. What's the biggest subarray here? Is it 8 or is there something better? I think that's probably the best one. All right, so let's try to solve this problem. Before doing anything clever, let's think about like a brute, it's called a brute force solution. So just kind of try all possible values. Try all possible solutions. For sorting, that's not realistic. You have n factorial possible solutions. Here, how many possible subarrays are there? N factorial, other guesses? 2 to the n, other guesses? Yeah. How many subarrays here? Remember, it's consecutive. Other guess? Well, so it's not about the largest one. or the value of just how many different subarrays are there. So here I drew you 3 subarrays. So this is a subarray, this is a subarray, this is a subarray, this is a, so all of those, then this, all of those are subarrays. Any guesses to how many? Yeah, so to define a subarray, I give you the start location and I give you the finish location. That defines the subarray. So this one is from position 1, 2, 3 to position 5. So if I give you 3 or 5, that gives me unique subarray. How many subarrays are there? Any guesses? Yeah. Yeah. Well, yes, but that's n squared. O of n squared. Yeah, I'm just looking for a big O answer, but that's it. So n squared subarrays. Choose first coordinate, start coordinate, then choose end coordinate. And choices for the first one, and choices for the second one, most n choices, so that's O of n squared. So if now so it's sort of, I can get a polynomial time algorithm just brute force with n squared, because I just have to check n squared values. N squared subarrays, check the sum in each. So check sum of each subarray. How long does that take? That's just a linear scan. That's O of n. So total time O n cubed. And if you're more clever about how you compute the sums, then you can get it down to O of n squared. Okay. But that doesn't matter. I don't want to go into those details because I want to do a much faster algorithm with divide and conquer. Okay. I want to do, I think it's going to be n log algorithm. So what could be a divide step here? What could be a divide? How could we try to divide and conquer this? Yeah. Excellent. Oh, okay, so we can search on the, we can divide this into half. So this is, we'll call this a left. This we'll call a right. And we'll find max subarray on the left and on the right. So what is, like, let's look here. What will be the max subarray on the left? Just 3, yep. And what will be this, the max subarray on the right? 7. And we already know that none of these is the optimal solution. Okay, so so the conquer step has to be a little more complicated. As you said, the problem is that there might be a solution that crosses the middle point. So for example, this one that we saw gives us the 8. So let me write that down. So the optimal solution is either in a left, in a right, or crosses the midpoint. Now, where are we headed with this? Let's try to write down what's our running time, T of n. We're saying we're going to make two recursive calls. 2t of each recursive call is n over 2 plus, so this is the time to find the highest, the best crossing, I'll call this crossing subarray. If we are aiming to beat this n squared time, what do we want in there? So if that takes n squared, if for example, if t of n equals to 2t of n over 2 plus O of n squared. Right, so by master theorem, the degree here is 2, log base 2 of 2 is 1. So this dominates. So this whole thing would be n squared, which is not good. I mean, this is what our brute force algorithm would have given us. So not good. But if t of n, if that term takes linear time, then this evaluates to, and this you've seen, this is the merge sort recurrence. So this is n log n, and this would be good. Right, so let's aim for this. We need a linear time algorithm to find the best crossing subarray. All right, so any idea of how we could do this? Anybody else? Go ahead. Can you? Okay. Yeah. I'd say, I wouldn't say going through, I'd say touching. It has to end at, so it has to end at the middle point here. And then let's try to extend. So if we go 1 in, we get an array of -2. If we go 2 in, we get 1. If we go 1 more, we get -5. And if we go 1 more, we get -10. So we can remember that the best we could have done is going here. Right? So we can remember that this would have given us 1. Now the same going right? We can say, okay, if we go 1, we get 7. If we go 2, we get 7 minus 6, 1. If we go 1 more, we get 3. And if we go 1 more, we get 4. The best we've seen there was a 7. And now we can combine those two parts. We can go left. We start from the middle, we go left one by one, and we keep track of the best running sum we have. Okay. When we take the subarray that gets us the biggest running sum. Then we do the same thing on the right. We start from the middle and we go right as much as we can. Well, we go right one by one and keep track of where we got the biggest sum. And that gives us a right subarray. And then combining those two, we get the best crossing subarray. Let me write this down in pseudocode. So find max left subarray given A and the midpoint of A. We keep a running sum, which is initially 0. And then for I mid down to 0, we update the running sum plus equals to AI. And we return the best running sum we found. This and the running time of this, well, you just have this loop, which is order n time. Inside this loop is just constant operation, and this is just a constant operation. So this is O of n time. Yeah. An empty subarray is valid. Well, yeah. Right. So let's so here's a 10, 11, 12. So say 1, 2, 3, minus 20, minus 21, 1, 2, 4. Okay, let's say this is your array. Right, and let's say these are your halves here. What's your best solution here? Probably this 1, 2, well, this 1, 2, 4. That's the best in the right. That's 7. I think that's the best one here. The idea these are so big that you never want to include them in any solution. So when you do when you're now doing this max left subarray, you're actually going to return 0 because when you start, the running sum is 0. And if you go, you get minus 20, and then you're still always going to be minus 20. In the right part too? Yeah, this is kind of a, well, in this case, the best sum is going to be just 1. So no, sorry, the best sum is okay. It's 0. Yeah. So okay, that's a question of, right, that's an interesting corner case. So I think we want to just say that there is such a thing as an empty subarray and it has some 0. And then, that will be the answer. Yeah. Oh, that's a, yeah, that's plus equals to. Let me clear that. Plus equals to. That's still. Right. So let me just give you the kind of the final algorithm pseudocode. So you have it. This one is, I don't believe this one is in the book. This algorithm is described in one of the recommended books, but it's not in the main book. So I'm gonna put so you have it here, I'm gonna put the actual algorithm down a little more precisely. So we need the middle point. Okay, so here, notice something interesting that I'm doing is I'm passing this A and I'm passing the indices into it. So I, J. So initially, I'm going to pass 1 and n, which is going to be the whole array. But then recursively, I'm going to make I and j to whatever I want it to be. So I'm not actually going to, I don't need to copy over this A every time I make a recursive call. I'm just going to pass it the implicit start and implicit end of the array. You'll see it in a second. Now we need the midpoint between I and j. This is just I plus j over 2, and we'll do a floor in case that's not an even number. So in this is just the average of I and j. So if it's one and n, then it's just it is the middle position n over 2. If it's somewhere else, it's just the middle position between I and j. Now I'm going to find recursively max subarray I to mid, find max subarray. So that was the left side. Now the right side, mid plus 1 to j. And now I'm going to find the find max left subarray ij mid plus find max right subarray ij mid. I'll call this A, B, C, and I'll return max of A, B, C. That's the algorithm, and the runtime. We already talked about it. So it's T of n. You make 2 recursive calls, each of size n over 2. And then the middle part, we talked about that it's O of n time. And this is then just log n log n. How many of you? Oh, question. Okay, good. Why am I passing 4 parameters here? I guess this assumed that the array is starting from 0. Well, actually, it shouldn't be 0. It should be 1 down to 1. So this function, when I wrote it, I assumed that the array was from 1 to n. But now we're actually passing it an array from I to j. So I can modify this code here. Let me actually just do it. So again, you have the complete. Let's put here that I'm passing I, j, and mid. Okay. Let me change my index variable here from I, because I don't want to crash with the other I. This is now a z. And let me, instead of going down to I, to 0, to 1, sorry, I go down to I. Does that answer your question? Okay. And I didn't write out the max right subarray because it would just be symmetric. It'd just be going from mid up to j. Okay, so I didn't write it out. Yeah, why do I mean? Yes, you could customize it. Yeah, you don't, in the left part, you don't actually use j. Okay, how many of you are very comfortable with this algorithm? Okay, how many of you are sort of how many of you are totally lost? Probably no one will admit it. But for those of you that are still any questions? We have time. Let me just briefly kind of summarize it again, because I want to make sure you get this. You'll have to solve a divide and conquer problem on the next homework. So yeah, so the problem is that we have an array of integers like this, some positive, some negative. And we want to find a consecutive block that has the biggest sum. And we're trying to find an algorithm that's faster than n squared, because I argued that n squared, I can just do kind of a brute force and naive algorithm and get n squared. So the idea is to divide the input into 2 halves, recursively find the solution for the left half, the biggest block there, biggest subarray there, and the biggest subarray in the right half. So this almost works, but not quite, because you might have that the biggest subarray is actually crossing the left and the right point, the left and the right block. Yeah. That's just a recursive call to myself. Right, I'm making find max subarray, so I'm making a recursive call to myself. Like Merzer, and then in that half, it's going to get half, and it's going to get half. So what might be missing, though, is something that goes through the middle, because then that's not necessarily, I mean, that doesn't show up as a subarray in any of the subproblems. Okay. So how do we find this? Well, it turns out it's easy to find because you know that it has to be crossing this point. We extend left to get the best we can for left, and we extend right to get the best we can going right. Right, that's what this max left subarray does, is it extends left to get the best we can do. And then max right subarray extends right to get the best we can do. So that the combination of going left and going right gives us the best we can do, crossing the midpoint. Now we have 3 possibilities. We have what we found on the left, we have what we found on the right, and we have what we found crossing the midpoint. And we just take the best of those. Questions? Okay, let's revisit the selection problem. Median finding and selection problem. How many of you are pretty comfortable with this one? How many of you are okay? Any particular place where we get there's confusion? Or am I gonna have to do a binary search through the? Okay, I'll do a binary search. So how many of you are comfortable once we pick the pivot? How many of you are comfortable with the algorithm, assuming somehow the pivot is picked? Okay, so even the part where I tell you, I've told you, okay, some way to pick a pivot. How many of you are still like unclear then what to do after you've picked a pivot? How many of you are super clear about that? I think I'm like losing people. So, okay, the idea here is the following. We pick a pivot. I'll walk through like from the beginning of the algorithm to the end. So I pick a pivot, meaning I pick a number from the input at random. Right. Let's say I pick, where's my input? Let's say I pick 21. I then count how many numbers are smaller than 21. I get 1, 2, 3, 4, 5, 6, 7, 8, 9. And how many are bigger than 21? Just one. So this is outside of the mid 50%. Right? I've got basically most of the numbers, like I guess 80% or something, 90% are smaller than my pivot. So this is not a good pivot. So I'm going to throw it away and I'm going to try to pick I'm going to pick another pivot. And let's say this time I pick a pivot 5. So 5, I count, I again scan to check if it's a good pivot. And this time it turns out there are 3 numbers less than 5 and 6 more than 5. So it's in the middle 50 percentile. So that's a good pivot. Now I'm going to stick with it. Okay. What I'm going to do then is count the number of elements smaller than 5, equal to 5, and bigger than 5. And then I'm going to check, okay, what's k? Well, I'm looking for like the kth smallest element. Depending on how k relates to those sums I found, those 3, 2, 6. Depending on how k is, I decide what to do next. I either, if I'm lucky, I can return that the kth element is the pivot is 5. Otherwise, I make a recursive call to either the smaller elements or the larger elements. To do that, like let's say I need to make a recursive call to the smallest elements, I go through this array again, and I construct this subarray of smaller elements than 5. And that's it. And when I'm in the end, when I'm an array of size 1, then I'm done. I don't need to make any more recursive calls. But maybe I don't even reach that at some point. Maybe I get lucky and the pivot I pick is actually going to be the kth smallest element. That's the algorithm. Now, it's a probabilistic algorithm, meaning that because I'm picking a random element for the pivot each time, I don't know exactly how long it's going to run. In the worst case, I could be picking a pivot forever and just being very unlucky. But here we do an expected case analysis and we count how many times am I going to need to pick a pivot before I get a good pivot. And that's where that lemma with flipping a coin comes in that says that I need to pick, on average, I just need to pick a pivot twice. So on average, in expectation, the second time I pick a pivot, I'm going to be finding a good pivot. Once we have that, then we can calculate the running time of the algorithm. So all these, picking a pivot, linear scan, these are all linear steps. And since we only do it on an expectation twice, then the total time to pick a pivot is also linear. And that's where this, there we go. That's where this comes in. The rest is the time needed to make the recursive calls. The recursive calls, here we use the fact that the pivot is good, meaning that even in the worst case, well, let me refine. What is bad for our algorithm? Bad is if we make a recursive call to a very large subproblem. Then we really didn't reduce our subproblem enough. So the worst case is how large is that subproblem that we create? Well, because we force ourselves to get a good pivot, then the worst that can happen is that the pivot is somewhere at the outside so here's the 25th percentile, here's the 75th percentile. The worst case is that the pivot is either here or here, right? Just right at the edge of those percentiles. And like, let's just say the pivot is here. Then the worst that can happen is that you can recurse on this half. It's not a half, but on the right part. And in that case, this is of size 3n over 4. And so that's really the worst that can happen. We go back here. That's where this term comes from. How many of you are comfortable with the selection algorithm problem? All right. More. Okay, that's it for today.